Hello, this is Young Pak. I am the Technical Marketing Director for Aerospike. Today we have a presentation that will be given by Anton Yazovskiy of Thumbtack. Today he's going to talk about a practical guide to SQL, the NoSQL, and migration. So Anton is a software engineer at Thumbtack Technology, where he focuses on high-performance enterprise architecture. He has presented at a variety of IT conferences and dev days on topics such as NoSQL and MarkLogic. So I'll hand it over to Anton. Anton?
Yeah, thank you for a great introduction. Hi, everybody. Thanks for attending. And let's start. So here's the meeting agenda. Webinar agenda. I'm going to go through all these bullets that I described here. First of all, I would actually give you a reason to switch to NoSQL. I'll try to explain you why you actually want to switch to NoSQL solutions. I'll explain you conceptual differences between your traditional relational data management system and NoSQL solutions. And after that, we'll actually go forward and discuss the practical questions, the practical steps that you have to ask, that you have to make in order to actually make this migration, right? So the first question, really obvious. Why do you want to migrate? We all love our relational databases. I'm pretty sure many of you heard that NoSQL solutions work fast, but could possibly lose some data. I'll let you explain why this is a myth. But many people just love the relational database. They have a good history that proves by millions of transactions, stable code mostly, support transactions, and they simply store the data. That's exactly what most people need. Also, they make concurrent access made easy. Most of SQL solutions provide C transactions guarantees that mean that you are able to, once developer says, store this data, the database will actually store it no matter what. That's what a C transaction means, right? And at the same time, programmers don't really need to be very smart about it. The relational database will take care of it. Well, you should be smart enough to start and commit the transactions, right? Or roll back in case of failure. But in general, it's very simple. And all the power of relational algebra and normalization forms allows you to create very abstract schemes that will be able to address most of questions that business may have. So why you would want to migrate? Obvious reason for migration to NoSQL is support of large volumes of data by running on cluster. Relational databases are not designed to run efficiently on cluster. I'm not saying it's impossible. I'm saying that it requires additional work, which means money for business, right? NoSQL, they're born to solve exactly this problem. Most of them scale out just out of the box. The second reason to migrate would be developer productivity. Schemaless allows developers to perform faster, which means that time and money for business. Also, in 21st century, very often data is semi-structured. For example, if you have to collect data from third-party servers and you don't really know exactly how it looks like, that's where schemaless could help possibly to solve this problem. According to CAP theorem, any distributed system trades consistency and availability. But most NoSQL are able to sit in many places in this trade. Just an example, Cassandra allows developers to tune consistency settings per request. So every request, developer are able to decide if he needs durability or performance. In this case, you can achieve to get best of both worlds to achieve better results. Another one reason, if you don't want to pay for something what you don't use, well, when all power of relational algebra is more than you really need, then, well, I love math, but I'm not going to pay for it. And the last one point is, when you want your data and applications speak the same language, mismatch between the relational model and in-memory data structures that developers use in applications confuse and fall to additional work. Object relational mapping frameworks make this process easier, but still it's additional work. So let's talk about a little bit about main conceptual differences between RDBMS and NoSQL. There are a lot of buzzwords around what exactly NoSQL means and how to describe the difference between them and a relational database. I'm not going to lie, this is not my idea, but I like how Martin Fowler and Praman Tedalach describe it in their book NoSQL Distilled. We may consider relational database as an abstract data storage. The right way of modeling a relational scheme, there is a ton of books around it, allows you to use particular part of your data in a very specific way. Those database represent a data storage that's accessible for many types of applications, usually developed by a separate team, and each of them could have a very specific use case. Thus, we can describe a relational database as an integration point between these applications and these teams, right, which operates with the same data set. And that's actually another reason why relational solutions have to be schema-full, because there have to be the rules common for all teams who use the database as an integration point. Integration database just can't trust every single application. On the other side, NoSQL data modeling is all about focusing on very particular need and goal. NoSQL data modeling is about preparing your data for particular specific use case in order to achieve better results. Thus, we may consider NoSQL database as encapsulated or application-driven. So this approach gives the developer great advantages. They are free to develop an application in a rapid way and at the same time focus on particular needs that business needs to solve. But at the same time, there is nothing for free in the real world. NoSQL don't do any magic. There is just a very simple rules. You take an advantage in one way and sacrifice others. I'm pretty sure you guys ever heard of cat theorem. If not, it's very simple at glance. Any distributed system is either consistent at any point of time or highly available, but never both of these characteristics. And a bit later, I'll talk about choices that we have to make when we migrate to NoSQL. So let's now, when I describe you what's the difference between NoSQL and traditional data storage, let's now talk about practical steps and best practice of NoSQL migration, NoSQL data modeling. Different databases are designed to solve different problems. Using single database engine for all of the requirements usually leads to non-permanent solutions, storing transaction data, caching session information, traversing graph of users, and the product they friends like or bought are essentially different problems. The requirements to analysis-oriented and transactions-oriented system are very different. Neil Ford created the term polyglot programming to express the idea that applications should be written in a mix of languages to take an advantage of different language that suit for a different problem. Similar, polyglot persistence is a hybrid approach to persist. You should understand that what type of tasks your storage should fit and choose the right solution for each of them. And by the way, I'm not saying let's store every record in separate database. It's nonsense. I'm saying let's choose the right solution to solve a particular problem. Here is an example of system that built following polyglot persistent practice. I'll discuss this system a bit later, but in the very first look, you can see that we define the different use cases, what we need in this system, and use particular solutions to fit these requirements. So I'm pretty sure you guys know all of this, but let me just very quickly go through popular NoSQL models. So key value represents pairs of keys and values. Most popular use case for such model would be metadata storages, sessions, URL parameters, HTTP headers, cookie matching, and so on. Key document, at first look, document is very similar to key value, but document is more about ability to operate with nested and hierarchical structure. Select and update particular pieces of your value of your document. Column family contains columns and related data. Unlike relational models, column family allows each record to consist of independent number of columns. So solutions like Cassandra are able to manipulate with millions of columns per single record. And the last one, graph database, represents entity and relationship between them. As an example, where it may work, it's like social graphs, roadmaps, and any structures where you need to traverse through a relationship between entities. So let's actually go to from theory, let's switch to practical questions and test what you want to ask and what you want to perform in order to actually perform your migration, right? That's why we're here. There's an obvious question that you have to ask yourself. We discussed it already, so I'll just skip this slide. I will only mention the last one bullet here. I have heard of it. And my favorite, I heard that developers love it. Yeah, that's a good point to switch to NoSQL. I'm joking, of course. So the first thing that you have to do is learn your traffic. You must have, there are a couple of things that how your traffic looks like. You may have only a few of these workload types, or all of them. I'm not saying let's choose one of them. I'm saying let's define how your workload looks like and what types of traffic do you have, so that you can choose the right solution to work with this kind of traffic. And at the same time, you have to take a look at your queries and the method, like the model of working with data, how your queries looks like. Are you only interested to simple lookups? You just don't really care of body of the records. You only need to take it and process, or you perform some inner requests, or you traverse graphs, or you make a certain search. That's all what you have to identify for yourself before going forward. Next step would be to learn a little bit about your data set, how your data actually looks like. I mean in terms of data modeling. It is just a simple key value, means every entity in your system represented by unique identifier, and you don't really care what is actually stored in the value. You only need the whole record for nothing. Or the data is structured or semi-structured, or you have a lot of nested and hierarchical data. For example, if you have a product catalog, most likely this is your hierarchical structure, right? And if you have a network of social relationship between your users, and you want to show information like what friends of your friends love or like, that's probably graph-oriented data. After you identify what kind of types of your data do you have to ask yourself what types of each data type do you have. This will affect the solution that you actually can choose. For example, some of key value storage works really well within a single server, but it's hard to scale them. So, and etc. As I already mentioned, migration to NoSQL is all about sacrificing something to achieve better results. That's why we're here. And there are a couple of questions you may ask yourself. First of all, I'll just really quickly describe what is a strong consistency means. Strong consistency basically means that if any point of time, all users of your database will see the same state of the data, and never they don't see different states of your data. But it's not actually something that we really always need. For example, if you are building a, let's say, blog post, you don't really care if readers of one of the users will see the blog post a couple of seconds after the user posted these blogs, right? It's not critical. And at the same time, if he just posted the blog, you don't see this blog, that's the problem that you have to solve. I think you got an idea. Another one question is transactional guarantees. Well, where you really need transactions, where you really need to, I understand that you never want to search your data, you would like to save them very safely, but it doesn't mean transactions. Transaction means update performs several operations as a single unit. It's not exactly what you need all the time, so you have to ask yourself where you can sacrifice where you don't really need it. And another one interesting question is about data losing. It sounds scary, like, hey, I'm gonna lose my data, right? But it's not that scary. For example, who cares if you have 0.001% of possibility to lose your session data? Nobody really cares. Like, I'm not gonna pay for it to get 100% of this possibility, right? So you also can identify these kind of use cases in your application. And the last question is sacrifice joins. Well, I'm not saying joins are impossible in NoSQL solutions. There are a couple of options. Probably some of you have heard of Google F1. They say that they solve this problem, but in general, NoSQL don't support joins, and you have to ask yourself whether you able to store your data together, denormalize. I'll talk about it a little bit later. In order to just don't use any joins. So, based on discovered answers, you have to define the most obvious type of storages that you may use. Here is an approximate list of solutions you may identify. Fast and simple lookup storages for non-critical data, and I would say that some of them actually persist the data, so you can use them. For example, Aerospike supports. I'm not doing an advertisement. I'm saying that these solutions support persistence. Relational data, or data that actually fit in the single server and that require very complex queries, which you are not able to express in aggregation or denormalization forms, probably should go to relational data storage. I'm not saying let's get rid of relational storage. I'm saying maybe let's take some use cases from it and transfer to NoSQL. Hierarchical structures, I just said that, for example, product catalog looks perfect for the document-oriented storages. You most likely want to use that for it. Because you don't want to perform all these joins in order to just simply read products, right? Any traversal, any queries goes to graph-oriented storage, no doubt. And the last one here, I'm not going to describe it in the details, but I want to mention it. There is a big data edge right now. It's a very hot topic. Most likely, most of you have heard of it. So, very often situation when you want to put your data somewhere in a highly scalable storage in order to perform their analytical jobs, for example, daily. In most cases, it's Cassandra or AGGREGATES or something similar. Okay, so let's take a look again at this picture. As you can see, the data structures involved in this process are very different. We identify that sessions, for example, are very simple. We don't care what stores in session. It's a key value, obviously. Catalog is the document-oriented thing. Financial data, 100% goes to relational database, recommendation to graph, and etc. I would also mention that here is another one type of storage, which not exactly NoSQL, but it's also part of polyglot persistent approach, the search engine. Some people like to use database full text search, but I think that in 90% of cases, special engine will solve this problem better than database. So relational modeling starts with the right structure of the data, and NoSQL data modeling are typically driven by application-specific query patterns. Instead of question, what answers do I have from my data? You should start with questions, what questions do I have, right? Yeah, and just in general note about NoSQL data modeling before we go deeply. Typically, it requires a deeper understanding of data structures and algorithms than relational. Normalization of your data is something that you will use all the time. It's your best friend. Hierarchical and embedded structures make your life easier, but at the same time, remember that you are creating distributed systems, so they are your worst enemy. Now I'm going to go through some examples of approaches and best practices of NoSQL data modeling. It could be a little bit too technical, but I just have to talk about it a little bit. So, before I start talking about this slide, I have to mention that theoretically joins is possible. I just mentioned it. But most NoSQL sacrifice joins, and developers have to pull data from database and intersect two or more arrays of rules in order to perform join. This is a technique that allows solve mismatch between aggregate and what data aggregate store and queries. In other words, when queries need more data than aggregate can provide. I'll talk about aggregate a little bit later. So here is an example. We have a user profile and we have an access object. In order to, if you would like to get more information about this access, you have to pull this data and join it in application code. So the main disadvantage of this technique is a chance to put your application in a situation where most of the data manipulation happens in application code. This should be tracked very, very carefully. If you have to perform in-application joins most of the time, this is a symptom that says that it's a time for data model refactoring. Imagine pulling 1 million records from each table in order to find a unique intersection. So that's a huge problem. And how to solve it? I'll answer on the next slide. So denormalization. That's a very, very basic technique that NoSQL solutions use. Duplication is one of the parts of denormalization. It's a technique of copying pieces of data between structures in order to either optimize query processing or convert data into a particular model which is close to your business. Compared to RDBMS, relational storages, most of NoSQL is a lot of join operations. Just because of nature of distributed system. Try to implement distributed joins in a relational database and you will understand what I'm talking about. Right? Alternatively, database can scan the whole cluster in order to find all pieces of puzzle. But obviously this is not the best approach because of performance reasons. Denormalization in general and duplication in particular allows to keep the data that you want to join in the same record and thus on the same cluster or on the same server. It's used selectively in relational database sometimes, but it's guiding principle in NoSQL. Let's go to the next slide. So, aggregates. Schemaless features of NoSQL allows to create as close to business domain objects as possible. What I mean by aggregates is a technique of embedding data structures into each other. Here are some advantages that you're going to get, and I'm not going to repeat it, but I will just point the last one about updates. By atomic updates, I mean an approach that allows to reduce damage of lack of transactions. So, this, if you have your data duplicated, if you store it together, then you are able to update this record after a single unit. Because most of NoSQL actually guarantee that updates will be performed automatically, atomically within a single record. And also many of them support check and save operations, so you are able to check if your data will be aggregated or not. So these two techniques basically go together very often. I just showed you an example, and another one example could be, for example, select a user and all associated comments with this user, or select a forum topics, and all associated comments. However, there are a couple of disadvantages. If you have your data duplicated, then updates of the duplicated part could be really big problem. We all know how it looks like in a source code if you have a copy paste in your source code, right? It's really hard to keep up to date all the pieces of this code, and very often developers just forget about it. Another one problem here is querying across aggregates, because it's heavy and complex. I'm not saying it's impossible. It's a very simple situation when most of NoSQL solutions provide secondary indexes or very similar functionality. I'm just saying that in this case, you're not asking particular node in your cluster. You're asking the whole cluster about the data because you're not sure where this record actually stores. You're asking across your aggregates. So developers should know domain and use case very well to define this aggregate. That's the key in order to successfully construct your model. Counters. Well, this is usually a record value or part of value in case of document-oriented and column primary solutions. They're similar to SQL auto-increment columns. In a highly available system, counters not always work as you want. Just remember about it. Let's assume you have a Cassandra cluster of 3 nodes with replication factor 3. It basically means that every single node has a full data set. You may want to perform increment operation and ask Cassandra for confirmation that this operation was actually successfully propagated across the cluster. But what happens if you got a failure? Does it really mean that all 3 nodes failed to increment counter? Or it just means that part of them failed, and if you will, should you perform incrementation operation again? Or this operation will increment value again? This is all detailed, but just remember to be careful with counters in distributed systems. Counter-type keys provide an ability to aggregate within single record 2 or more related pieces of data. What you do is you combine IDs of these pieces of data together in order to create unique identifier in a united record. Here is a practical example. You have a distributed cluster, but full of user profiles, right? So distributed system and a lot of user profiles stored across this cluster. You need to implement chat between any 2 users from your data set. Let's say profile of user 1 stored in server 1 and profile of user 2 stored in server 2. How will you model it? Where you will actually store the log of their messages? Well, that's where COMPOSITE keys can help, because this is an aggregate, as we discussed before. It will be very easy for database to scale the solution automatically. As you can see on this slide, we created a united record, which consists of each user IDs, some prefix, and probably timestamp, which is not really required, but just in case if your chat will be too long. And in this case, you have united record, which stores in one single server and will work and scale automatically by NoSQL solution. Well, by most of them. But there is another problem. How do you perform an update of this record? Let's say both users send a message at the same time. Developers can just read, update value, and write it, because in this case, there is a possibility to lose another message, right? Hopefully, most of NoSQL solutions support the data modeling practice that I'm going to discuss next. Because most of NoSQL solutions have a lot of transactions. A very popular way to allow concurrent operation is appending. This approach mostly applies in document-oriented and column-oriented data models, but not in key value. Well, there are a couple of options to use this approach in key value, but really few of them. Solutions like Redis or Aerospike allow to append even more. Some of them support big data type, and it's very convenient for this kind of tasks. Another example would be taking into account our previous slide, let me slide back. If one of the users send a message, instead of read, update, record, and write, you will just append the data. And in this case, you're not gonna miss the data, right? You'll just append there. You're not overriding anything. Here is the key thing about it. Another example would be financial operations, which are just represented on the slide. Let's say user A has an account with $100. Of course, I'm simplifying. In order to put a deposit of $10, we have a couple of options. Read, modify, write operations, what I just described, which have to be synchronized and most likely slow in case of concurrent access. Another one approach would be keep tracking changes of the account instead of total value. In other words, append the changes of total value to the account record. So once we apply one of these or all of them data modeling practice, we can think about what to do next. The next question that you have to ask yourself is, what parts of your data have to be in sync between each other? For example, if you have a cache and user profile in your main database, most likely you want to update this cache when you update your user profile if you want consistency between them. Sometimes you don't, but that's the question of your business logic. Another one example could be if you have a social graph, for example, and there are some duplication of the information there. For example, user name. And user updated his name in a relational database where you store user profile. Probably you have to update this information in a graph storage as well, just because you use the data for example, showing something on the page. User will be really confused to see that he updated the value, but it's actually the old still. Here's a couple of approaches that you can use in order to keep your data in synchronization. First one is basically application level. In your code, very simple. When you update the data in one storage, you as well update data in other storages. Depends on your logic. If you perform an update in MySQL, you as well go into MongoDB and update some value there. Or if you perform updates in Couchbase, so it goes to Solar or Elasticsearch and reindex record there as well. The disadvantage of this approach is that this request has to be synchronized because it's all or nothing. If you fail to update the rest of the database, you will lose this information, right? Another one, two options would be actually will help you to solve this problem. First one is just a regular synchronization. In case consistency is not something that you need, you can just run like daily or hourly jobs that will take the updated data and propagate it across your other storages. Very often it works. For example, if you have a relational database that stores your metrics, some statistics from the system, doesn't matter what exactly. And you have a log that represents user actions, which stores in, let's say, Cassandra, because it's highly scalable and there are a lot of traffic. You don't really care about consistency. You're okay, you're fine to update these metrics, let's say, every 30 minutes or every hour. In this case, you'll just run regular synchronization. That's what you do. But that's all about like how much inconsistency you're able to get in your application. And the first one, options, is actually about helping you to solve this problem. It's kind of best of both worlds from application level synchronization, which allows you in real time consistently update everything, and regular synchronization in background, which means that you have inconsistent state of your system, but the load on the system is less. Incremental background synchronization basically means that in background, somehow, I'll describe how exactly a little bit later, you track changes that happen in your database. For example, if your main database is MySQL, you're taking a look at the MySQL transaction log, for example. and apply the changes to the rest of the storages. Good example could be if you have a user profile from MySQL, you have a constant replicator configured to work with MySQL. This tool just take a look at the transactional log and do exactly what I just described. It takes the updates and apply them to, let's say, if you have a cache of these profiles in Aerospike, which use by edge server or any system that needs a fast lookup. You'll just perform this incremental updates there using Tungsten. So let's take a look again on the system that we discussed during this presentation. On the top left part of the slide, you can see the most traditional version of e-commerce system. Like 10 years ago, 5 years ago, it was happened all the time. People just use relational storage everywhere. In some cases, sessions and shopping cart, they're moving to Memcache. Great, that's a good thing. That's a good first step. And if you apply all the approaches and all the practices I just described, first of all, you identify that you actually have a different traffic. You have different data, and you need different guarantees from your storages. If you apply it one by one, you'll get the system that you can see on the bottom right side of the slide. As you can see, we use particular solution to solve very particular problems. We don't load whole traffic on our relational storages because we don't really need it. That's the key thing here. So I just want to quote myself once again. No matter what you do with data modeling, you have to remember that in most cases, you run queries and your model will be stored in distributed system in the cluster. So all your decisions have to be made based on this information. I just want to thank following people and authors. I took the information from there. They have very nice blogs, and the first one book that I mentioned, I really recommend it to you. NoSQL Deflated, it's a great book. And it will help you with your data modeling. Thank you.
Okay, Anton, thank you very much. Very informative webinar. What we're going to do now is open it up to some questions. So as the questions come in, I'll read them off to Anton. And while these are coming in, let me just start with a couple of my own. So we know, for instance, that there are different reasons why you might want to move from a single SQL relational database to a polyglot of different other databases. So NoSQL being prominent amongst them. Are there specific use cases where you see a lot of this kind of motion?
Just to confirm, you mean that if I see any use case where relational database is better than NoSQL?
No, sorry, where people are moving from a relational database to NoSQL databases.
Yeah, that's basically what I just described. You have very specific use cases. If you are willing to sacrifice some of your functionality in order to achieve better results, that's what you're going to do. But at the same time, there are a couple of use cases where relational database is better, obviously.
Okay.
For example, go ahead.
No, go ahead. Sorry.
Yeah, I just want to say that, for example, if you don't really know how your queries looks like, as I said, NoSQL is about focusing on solving particular needs and solve it very well. If you don't really know how your query looks like, if you have a lot of applications working with your database, and which is very important, if your data fit in the single server, probably a relational database is all you need.
Okay. All right, and so another question here is, have you noticed any trends in the amount or use of OLTP data?
Yeah, absolutely. We are living in the 21st century. People use internet all the time, and Domain areas like tech or finance, they grow like crazy. And during my practice in Thumbtack technology, I see this all the time around. Very short transactions very often apply to the people's life. But at the same time, I want to mention that these short transactions actually create a big data. If you want to store this data somewhere, once you process it quickly in a transactional, in a solution that allows you to process these quick transactions, you want to store it somewhere. And this is another part of the problem. That's why big data is so hot target right now.
Okay, great. And so we have a question here. Are all of the NoSQL solutions discussed here, do they suffer from the same RPC timeout error trying to get relatively many rows returned?
Can you paraphrase it somehow? I didn't really get a question.
Sorry. So of all of the NoSQL solutions that you've discussed, do they suffer from the same RPC timeout error when you're trying to get many records at the same time?
So just to confirm that I got the question correctly, the question is how this solution will perform if you're going to get a lot of data at the same time, right?
I believe that's it, yes.
Yeah, okay, well, I believe this is not about NoSQL. It's about just in general about databases. If you're going to select 1 million records from a relational database, and specifically if you have a cluster of them with sharding and duplication, you're going to get a huge problem. It's not a question of your storage, it's a question of your architecture. And you have to solve it there.
Okay. All right. And are you seeing a lot of people who have decided to go with a more vertical scaling? You know, they might have started with a MySQL or an Oracle instance, and they've increased the size of that single instance. What typically is the breaking point? Why do people move from that to another one?
Sure. So here are the two questions. First of all, it's really true that people do that, and the answer is very simple. Yeah, I've seen it all the time. Why people do that? Why people do vertical scaling? Well, because there are a couple of reasons. First of all, very often you really need if your data source is integration point, it's hard for you to convert it to service-oriented, to define the use case and convert your system to service orientation. People think that it's cheaper to buy the servers, right? And but it's not going to happen all the time. At some point, you just will get to the situation where hardware costs up to so much that it's cheaper to scale out than scale in. By scale out and I mean add more servers if it's scale out, or more servers if it's scale in.
Okay. And then there's one more, there was a complementary question on the RPC timeout. So for instance, Cassandra will refuse to return rows if it takes too long. Is there some mechanism for dealing with that, or do some databases handle this better than others?
Oh, now I got the question. Well, most of the NoSQL solutions actually provide you an ability to select some kind of timeout. So yes, short answer, yes, it's possible. Which solution do this job better? It's a religion question. My answer would be you just should use your database correctly. You should use all the advantages that it gives you, and in most cases you are able to set up some kind of timeout for your query. And then on the client side, it's a question of your application call. But as well, some solutions allow you to add and cancel query processing. So I'll just name all of them, like Couchbase, Aerospike, MongoDB. Almost all of them, they support timeouts. It's just a question of how you use that, if you use it or not. And the second part of this problem is, again, this is a question of architecture. Why would you need so much data that can throw timeout exceptions? It smells like a bad design here. I understand that it's a real world. Sometimes it happens. But I'm just saying you should take a look at your code and your logic.
Okay. Okay, I think that's pretty much all the time we had for questions here today. I wanted to thank you, Anton, for the great webinar. What we are going to do, Aerospike is going to package this up so that if you want to watch a replay of this webinar or if you want to let other people know about it, we'll have it available on our website, on our webinar page. And I'd like to thank you all for your time. Thank you very much.
Thank you, guys.